Where does my current phasor for the resistor go?
Along the voltage.
Yeah, they're in phase, and so I'll draw that there, and this is the current for the resistor. Where does the current phasor for the capacitor go?
$90.
For the capacitor, which one leads?
The current.
Current leads. So, no, the capacitor leads. Remember, this thing is zipping around this way. It's the one in front, so it would be over here. I don't know whether IR, IC should be bigger, but I've drawn it as such. Again, the reason, if I drew them the same length, when I then add them, then the sum is going to be on the axis, and that's what I'm trying to avoid. I know that the current coming out of the power supply splits. And so the current going across the resistor plus the current going across the capacitor should add up to the current going across the, coming out of the power supply. And so the sum of these two currents gives me the current coming out of the power supply. Something like that. That is the current from the power supply. I have drawn it worse, which is not much consolation. But the current coming out of the power supply squared is equal to IC squared plus IR squared. And so now we go through our bit. I know that for a resistor, for a capacitor is equal to Ix sub C. For an inductor, it's going to be Ix sub L. We haven't done that formula for X sub L yet. And for the power supply, it's going to be equal to I times C. So current is just the voltage divided by the impedance, reactance, resistance, whichever one it happens to be. So this will be the voltage from the power supply over the impedance squared is equal to the voltage across the capacitor over the capacitive reactance squared plus the voltage across the resistor divided by the resistance squared. All my voltages are the same because they are in parallel. And so dividing that out, I get 1 over Z squared is 1 over X sub C squared plus 1 over R squared. Square root of both sides, I get 1 over Z is equal to the square root of 1 over X sub C squared plus 1 over R squared. Or Z, for this case, is 1 over the square root of 1 over X sub C squared plus 1 over R squared. That should be X sub C there. And so we have a different formula for impedance because, again, impedance is specific to a problem. Now, some textbooks will give you a formula in the summary section, will give you a formula for impedance for the RLC circuit. The one they usually give you is for R, for resistor, capacitor, and inductor in series. But just be careful. If you ever get a formula page with a formula for impedance, please recognize that is only for a specific case. Despite what some students have tried to do, where they just sort of, anytime they're asked to find impedance, they just plug into that formula and see what you get. We can find these are out of phase. So if this is considered to be phase of 0, this is phase of pi over 2, so it's plus pi over 2. Notice we have this cosine omega t here. So if this is cosine of omega t, this would be cosine of omega t plus pi over 2. And this, well, how much is it? What is that angle right there? Oh, I have some clues here. Oops, so not that angle right there. I have a right triangle. That's a right triangle right there. I know that the tangent of phi is the opposite, which is I sub c, over the adjacent, I sub r. Something darker, there we go. So the tangent of phi is I sub c over I sub r. I sub c is equal to, well, we just did that over there, is the voltage across the capacitor divided by X sub c. And for the resistor, the voltage across the resistor divided by the resistance. Again, the voltages are the same, they cancel out. What we're left with is R over X sub c. And that's going to be R over 1 over omega c, because capacitive reactance is 1 over omega times capacitance, which is just equal to omega CR. Again, this is specific for this problem. Yeah. So if we assume omega to be 376 point something, whatever it is for us. So 376 radians per second. Resistance of 1,000 ohms. That's not the sum. 1,000 ohms. And let's throw an extra 0 in there to actually make it 1,000. And capacitance of 15 microfarads. Is that going to come out nicely? Three. I'm doing it in my head, so well, we'll find out what happens. So the tangent of phi is omega, which is 376 radians per second, times my capacitance, which is 3 times 10 to the negative 6th farads, times my resistance, which is 1,000 ohms. What do we get?
.128.
Units?
Radian farad ohms per second.
Which is the equivalent of?
Amperes.
Pardon?
No. Yes, amperes.
No.
No, I was wrong.
And you were right when you said no earlier.
Yeah.
We're doing a tangent of an angle. What are the units of tangent or sine or cosine?
Radian?
No.
No.
Well,
Degrees.
so that's the angle. The angle would be radians or degrees. What is the trig function?
Doesn't have.
Yeah, doesn't have units. A radian farad ohm per second is a 1. All right, so phi would be
48.
48 degrees, and how many radians is it?
$1.55. Maybe,
No. 1 radian is 50 something degrees, so it has to be less than 1.
0.85.
And so this angle right here is 0.85 radians.
How do you repeat that?
Arctan, tangent of phi is equal to this, and so if you want to isolate this, you have to get rid of the tan and do that with arctan or inverse tan.
You have to change it to radian though, right, in your calculator.
Yeah, or get this and then convert at that point.
How do you write that down?
180 degrees is pi radians, or 360 degrees is 2 pi radians, and so that's the conversion. So if I, in degrees, I multiply times pi over 180. Degrees to radians. And the clock says it's time to go.